Amongst the team designing the FRGB instrument lights, we have two computer engineers and two electrical engineers. The two computer engineers consisted of Leif Rabat and Carson Warner, and were in charge of handling the software of the project, while the electrical engineers consist of Anya Frohak and myself, Stefan Gonzalez, and were in charge of the hardware aspect of the project. Our project is the Frequency Responsive RGB Instrument Lights, also known as FRGB lights. These RGB LEDs are designed for musical instruments. The LEDs are controlled by the frequency and volume of the instrument being played, where the frequency determines the musical note, which in turn determines the color of the LED, and the volume determines the brightness of the LED. The main goal is to create an immersive visual element to musical performances in order to better captivate a wider audience. These lights can be used for a wide variety of performances, such as recitals, concerts, parties, and even the topics such as giving people a visual representation of a symptom of synesthesia, which is a visual disorder. With this product, we hope to give the music genre a new advancement in the modern era that will bring in new members. The design specification of FRGB instrument lights consists of four main points: two hardware objectives and two software objectives. For the hardware objectives, the project needed to have a signal-to-noise ratio value of 25 decibels, and the portability was predetermined to be under 3 pounds and under 7 by 5 by 5 inches. Reason being is that the device has to be easily transportable and accessible to use on short notices, and with little setup time. Continuing on with the specification is the software objectives, which is the refresh rate being at least 5 iterations per second, and to have a fully customizable setting for the musical notes and their colors. Having a signal-to-noise ratio of at least 25 dB was a key specification for our printed circuit boards. After receiving our PCBs, we attempted to calculate the SNR using a spectrum analyzer. However, we ran into trouble while trying to find the signal of our circuit, as it would not display this on the spectrum analyzer. After consulting with the lab manager David Douglas, we were told that the frequency we were working with were too small to display on the analyzer, and using it to find the SNR was not a viable option under his expertise. He then suggested using a decibel reader. However, the labs did not have any dB readers for us to use, which was a large hurdle as this meant we would not be able to calculate the SNR, which was the most important specification for our hardware. So after further consulting with David Douglas, he informed us of a new method to find the SNR value by using the HMC 8012 digital multimeters that were available in the lab. This method, albeit not as accurate, gave us a general idea of our SNR value. With a noise value of negative 144.5 dB and a signal value of negative 78 dB, our signal to noise ratio resulted in a value of 66.5 dB. This value is over 2 times the minimum value that we set as goal at the beginning of our project. We would like to mention that we theorized that our actual signal to noise ratio is closer to 80 to 90 dB, as that is what is stated in the datasheet of a 16-bit ADC datasheet.
From the beginning of our research, we had intended to have a minimum refresh rate of 5 iterations per second for our program. Through various testing and constant trial and error of various sample rates, we have achieved a sample rate well above what we had intended. Our stretch goal was a minimum of 10 iterations per second, which we also achieved. However, because the video does not clearly show every iteration, we will show proof of 6 iterations per second. The video on the right is an example video that clearly shows the 6 different iterations. The first 3 iterations are changes in brightness with the first color, and then it displays 3 more iterations that are the changes in colors. The clip has more iterations, such as when the lights are displaying the color blue, it goes through a couple changes in brightness. However, it is difficult to claim that they are iterations and not camera adjustments in the video. The biggest goal we had for the software was to give the user the ability to choose what color will go with each individual musical note. We wanted the product to be fully customizable. By applying a Bootstrap library into our Python GUI, we managed to create 12 buttons, one for each musical note, that allows the user to select and set any color they desire from a pop-up RGB spectrum. The image displayed shows what our program looks like after having selected the colors of each note. As you can see, the program also displays the selected color under the button for each note. From here, the user will simply set their custom theme and continue on to the next screen where they can begin their visualization.
For our hardware block diagram, we have three segments. First is the instrument, which has the LED lights attached to it and feeds input into the microphone. Next is the amplifiers and connections. And the third is the box, which contains the ADC, the LCD screen, the power supply, and the microcontroller, which receives and sends data and power throughout the block diagram. For the software block diagram, we have three segments as well. The Python driver code, which reads the input signals, does all the mathematical calculations, and then outputs the results to the LEDs to change their color and brightness, and the UI, which is displayed on the LCD screen for the user's convenience.
Here we have the microcontroller comparison table. This table shows all three options of the microcontrollers that we considered for this project. Starting with the Raspberry Pi 4, its cost is $158. Its processor speed is relatively fast in comparison to the Raspberry Pi 3 and NVIDIA Jetson Nano. The Raspberry Pi 4 has 2 GB of RAM. The size of the Raspberry Pi 4 is very similar to that of the Raspberry Pi 3 and NVIDIA Jetson Nano. And similar to the other options, the Raspberry Pi 4 has 5V DC power input. Next up, we have the Raspberry Pi 3. If it can be found in stock, the price of the Raspberry Pi 3 is $80. Out of all the microcontrollers, the Raspberry Pi 3 has the slowest processor speed. The Raspberry Pi 3 has 1 GB of RAM. Just like the Raspberry Pi 4, the Raspberry Pi 3 has a very similar size to all the other microcontrollers in this comparison, and also uses 5V DC input. Next up, we have the NVIDIA Jetson Nano, which costs $298. This is the most expensive out of all of the three microcontrollers that we compared. The Jetson Nano has the fastest processor speed out of all the microcontrollers. In terms of RAM, the NVIDIA Jetson Nano has the highest capacity of all three microcontrollers. The NVIDIA Jetson Nano has a very similar size to the other microcontrollers in this comparison. It also uses 5V DC power input. When taking into account all of these attributes, we ultimately went with the Raspberry Pi 4 due to its relatively low cost and overall community support.
When looking at ADCs for this project, there were multiple architectures considered, especially since originally we were trying to design our own. For our application, we needed to make sure that it had at least 16-bit resolution since we were working with audio signals. Dual slope, while it has the accuracy we wanted, has a very low throughput due to the internal timer having to reach the max threshold and back to 0 each cycle. Flash architecture for high accuracy applications is very expensive due to the fact that it has to have 2 to the 16 comparators for 16-bit applications. Pipeline architecture, while fast, was quite expensive, as it still requires 60 comparators for the resolution we required, and added the most noise into the system. The Delta Sigma architecture was the most affordable for the resolution we needed, and included noise shaping to reduce quantization noise. Successive approximation architecture had low noise and higher throughput, however was more expensive. This led us to choose the Delta Sigma ADC for this project.
Here we have the comparison of the LEDs. The two types of LEDs that we compared were the SMD and Cobb LEDs. The quality of light for the SMD LEDs is not perfect, as they introduce glare. In terms of cost, the SMD LEDs are 5% higher on average than the Cobb LEDs. The SMD LEDs introduce full color adjustability in comparison to the Cobb LEDs, which do not. The SMD LEDs have a brightness of 50 to 100 lumens per watt. Next we have the Cobb LEDs, which feature no glare and have a uniform light beam in comparison to the SMD LEDs, which do not. Overall, the Cobb LEDs are 5% lower on average than the SMDs. Unlike the SMD LEDs, the Cobb LEDs do not feature color adjustment. The Cobb LEDs have a brightness of 80 plus lumens per watt. Ultimately, we chose the SMD LEDs due to their color adjustability and high brightness. In this section, I'll be going over the process involved in converting music input into color. To achieve this, we utilize Python to convert audio input into frequency values in Hertz using the PyAudio library. After we gather the frequency of the audio input, we then utilize a lookup table to assign ranges of frequency values into notes of the chromatic scale. Subsequently, these notes were assigned to unique colors. This process helps convey a visual representation of chromesthesia, which is a unique function of the brain in certain individuals that lets them correlate sound into color. After the base program was established in Python, we implemented note-to-color relationships. Note-to-color relationships assigned specific notes with specific colors. For example, if we were to play the note A flat and it was assigned to the color blue, then our output for the LEDs would show the color blue.
This is the first design attempted, which was designed by our team. It was designed based on the basic building blocks of a Sigma Delta ADC, such as a difference amplifier, integrator, clock, comparator, and digital filter with I2C to communicate with the Pi. It is also second order, so it repeats the difference amplifier and integrator stages to achieve a higher resolution with less oversampling. The difference amplifier subtracts the feedback from the signal coming in. The integrator then does noise shaping to push the noise to higher frequencies that will be removed by the filter as the output to result in very low quantization noise. The comparator, which acts as a 1-bit ADC, outputting a 1 if it is greater than 0 and a 0 if it is less than 0, then through the D flip-flop to add the clock signal into the output, and a switch to invert the D flip-flop signal as the component we bought only had Q bar. The digital filter then decimates the signal to bring the output of the signal to a usable frequency, and it filters out the high frequency noise as we only need up to 20 kHz, as this is the highest a human ear can hear. Most signals that we expect from the mic will be much lower than 20 kHz as well. This is the output of the original ADC when bypassing the op-amps used for the difference amplifier and integrators. The input signal of a triangle wave is in yellow, the comparator is on in purple, the switch in green, and the D flip-flop in orange. These were all working as expected from the simulation. The op-amps, however, were not. This is most likely due to the simulation using ideal op-amps. When testing this one, we were not using bypass capacitors on any of the power supplies on the op-amps, which may have added noise and contributed to them not working. Another reason that we learned when testing the next revision was that we needed to use different op-amps suited for each function, which was not done for this attempt. We just used the THS 4222 GGK. However, throughout testing, we tried 4 different op-amps, and none of them worked as simulated. We also had to use a different D flip-flop than originally bought, as it was a 16-pin D latch, because when buying parts, as we hadn't used DigiKey and were not able to find the smaller D flip-flops needed for this application on DigiKey. We also could have not been using a high enough clock signal, as the second circuit tested used a frequency 12 times greater than the 5 MHz tested with this design. The original comparator of the MAX 907 EPA Plus also did not work as expected. However, when testing the 4 other comparators, the TLC 3702 CP worked much better. Overall, we were not able to find the conclusive problem with this circuit, as there were too many factors and it could have been the design itself. We were recommended to find a design that had been used and tested before. This is the second design attempted, as this one was a project previously done at MIT and had worked before. We misunderstood the advice given to us from Dr. Wei, which was to find a project that was previously done to find a reference design to build. This would have guaranteed it worked, and there would have been exact parts and test data to reference. This uses the same concepts we used previously on the first design with a difference amplifier, integrator, and comparator. However, instead of a D flip-flop and switch, they used a sample and hold circuit with MOSFETs instead. It also added voltage buffers to prevent the circuit from breaking. This design had the opposite problem of the first attempt. The op-amps worked and the comparator and clock didn't. The oscilloscope reading shows a sine wave of 20 volts peak to peak at 60 Hz in yellow, the difference amplifier in green, the integrator in orange, and the output of the sample and hold circuit in purple. The difference amplifier's output was different as the feedback loop was incorrect. This is due to the clock not being input into the system, as none of the buffers were working as expected. The clock buffer outputted nothing, so the output of the sample and hold circuit, which should have been oversampled at a rate of 66 MHz, was only at the 60 Hz of the input. This caused the rest of the circuit to output incorrect voltages. This could have been because the buffers used in the schematic were discontinued, so they were replaced with the buff 643 AIDR, as recommended by DigiKey and research. It had a minimum bandwidth of 35 MHz, which made it much harder to test, as the oscilloscope and function generator only output up to 20 MHz. We tested if the clock was the issue, and it outputted a signal closer to a triangle wave. But after testing and more research, we discovered that is how clock signals look when in the 66 MHz range, and it was indeed correct. Since the deadline was quickly approaching, we asked Dr. Chan, and he recommended to just buy an ADC and to use that instead. This is the ADS 1115 QDG SRQ1, which is the ADC we ended up using for this project. This decision was due to the fact that this ADC has a library for the Pi and a pre-built module we could test it against. This was important as the only output was through the Pi using the IGC pins, and the previous problems we had testing the other two ADC circuits. We originally were using 5 volts for the power supply, but upon further research learned that the Pi's GPIO pins only take up to 3.3 volts, so we are powering it with the 3.3 volts from the Pi instead, and amplifying the microphone signal to about 15 times to the 3.3 volts peak to peak. As shown in the right picture, the yellow is the clock coming in from the Pi SCL pin, and the green is the digitized PCM signal from the analog microphone input being communicated to the Pi using the SDA pin.
The preamplifier schematic was based on the reference design for a non-inverting microphone preamp from Texas Instrument. With the microphone and gain specification calculated, we got the design on the left figure. This design raises the output of the microphone from mic level to a voltage that the ADC can use. As mentioned previously, we originally were going to use a gain of 50 to bring the microphone up, which originally we estimated to have a max voltage of 100 milli VPP, up to 5 VPP. However, we had to bring that down to 3.3 VPP based on the accepted voltage of the GPIO pins on the Pi. When doing that and remeasuring the microphone outputs, we realized the peak voltage could go higher than the originally tested 100 mVPP. This caused us to redo the calculations and go with a much more conservative gain of 15, which avoids any chances of clipping. We originally thought to increase the signal as much as possible so that the ADC would have a higher accuracy, as there would be less of a question on if it was above or below the reference voltage. However, through testing we learned clipping was happening too frequently, so we went with a smaller gain when we were doing the calculation. Thankfully, the gain is controlled by the positive feedback resistor, which was changed to 3.3 kiloohms. Our project included the use of a 3D printer with PLA material. In the fabrication of our design, the team's hopes were to secure the sensitive components within the project's design box in the most efficient manner to ensure the project's performance to be in accordance with its senior design specifications. In the case of this project, it was desired to be lightweight and compact enough for a user to move at ease. As the project experience changes over the course of senior design, so has the overall schematic. As seen, the box is no longer a one-to-one copy of the original SOLIDWORKS design, reason being that the original design was no longer compatible with the current version of the project. With the introduction of new circuit boards and connections needed, this created a need for adjustments on the design of the container, such as port openings, drilling holes, and proper mounting of screws on the container to secure the hardware and electronics. This was all done to ensure that the device can be moved around in any vector without the concern of electrical disconnections or short-circuiting of components.
Here we have the layout of the Raspberry Pi 4B and its pinouts. For our project, we needed to use 3 ports and 6 pins. The required ports we used are one USB 3.0 port for the microphone connection, a USB-C power port to power the system, and a 2-lane MIPI DSI display port for the LCD screen. The required pinouts are the 3.3 volt power pin to power the analog to digital converter, the GPIO2 SDA pin, and a GPIO3 SCL pin to connect the ADC to transfer the data, the GPIO18 PCM clock pin to send data to the LEDs, and 2 ground pins. All of these connections are hidden away behind the touchscreen of our box.
This project consisted of 2 circuits to achieve its main objective as shown in the 2 figures displayed. The preamplifier and the ADC are key components for this project. The schematic on the top left is the preamplifier, which receives signals from the instrument, amplifies the voltage with a gain of at least 15, and then sends the boosted signal to the analog to digital converter, which is the schematic on the top right. The ADC converts the signal produced from the preamplifier to a digital signal that can be received by the Raspberry Pi 4 microcontroller. The Raspberry Pi 4 microcontroller is also receiving a direct current of 5 volts, which is being powered by a wall outlet. The Raspberry Pi is acting as the heart of our project, which does all the mathematical calculations once the signal is received and then sends desired output data to the LED strips, which will cause a change of brightness and color.
To convert our input voltages into frequencies, we utilize the Fourier transform. The Fourier transform is an algorithm designed to interpret repeating patterns and is applied in sound, optics, and electrical engineering. The Fourier transform finds the frequency of the fluctuations and converts a sound into a list of frequencies. These frequencies can be correlated with individual notes. The Python application uses the fast Fourier transform library to implement fast Fourier transforms. A fast Fourier transform is an algorithm made for quick computer calculations. Here, we're going to review the GUI for the Python program. The GUI of the program has 3 separate screens, the first of which is very simple and allows the user to select from a list of themes and continue to the next screen. This next screen shows the customizable theme menu, which allows the user to select colors for each note to customize their experience. After the user is done selecting notes, they can select Set Theme and then continue. Lastly, we have the main visualization screen. This screen houses 2 widgets that update in real time. Once the user starts visualizing, they are greeted with a dial-like volume readout that shows volume in real time, and a note readout that shows the current note being played. From here, the user can restart the program if they wish.
The following images represent one of the classes in our Python program that we had written to test our product throughout the developmental phase of our project. Since we were meant to be working with another computer science team, our program is a simplified version of what they had created, despite us having written our respective programs in different languages. You can see in the image on the left that we utilized the PyAudio and NeoPixel Python libraries. These libraries allowed us to read in the sound frequencies and control the output of the lights, respectively. We then read the data, conduct a few calculations, and then, as seen on the image on the right, assign each frequency to a specific musical note. The final version of this code also included setting the gain, a few more mathematical calculations, and the GUI. We also needed to use the tkinter and ADS 1115 libraries. These libraries helped us create our GUI and communicate with our ADC, which is the first thing the program does. The program does many calculations, including the fast Fourier transform shown in the image, in order to obtain the volume and convert it to an integer value from 0 to 100. This value also determines the brightness of the LEDs. The following 2 images represent an early test of the Python code shown in the previous slide. The image on the left shows the microphone reading the same note over an extended time period, while the image on the right represents the microphone reading multiple different notes over a short time period. You can see how the output tells us the frequency of the noise emitted along with the musical note it corresponds to. In future tests, we also used the terminal in the same way to have the program tell us the volume of the noise being read by the microphone. This allowed us to confirm that we were reading the correct musical note and the volume without needing to connect and run the entire device. Another test we used was using speakers to output a specific musical note's frequency and comparing the frequency we were outputting with what our program was displaying. Once we saw that they were the same, we had the confidence to move forward with our project without worrying that our software could have been the issue.
The first challenge faced was the goal of designing ADC to build. In the fall semester, we hadn't realized how hard of a feat that actually was to do, as well as the nuances with the different parts of a Sigma Delta ADC. We spent the first 3 months testing the first ADC, which we designed ourselves. However, it was eventually decided that the goal was not able to be reached within a single semester, and the experience level that we were currently at. The second challenge was shipping delays with the PCBs. As we spent so much of the first semester trying the first ADC, when it came time to order the PCBs used for this project, we had less than 2 weeks before the deadline. Therefore, we had to pay the fastest option of 4 to 6 days shipping, and that still got slightly delayed. The third challenge was component failure. This was due to problems while testing, such as misplaced wires or errors with the circuit design, which caused overheating on multiple occasions. This was solved by ordering extra of every component to use as backups, so testing wouldn't be delayed further. The fourth challenge was understanding data sheets. When beginning the project, we hadn't had the experience to know what values we should be checking for each component to ensure that they would work for the application we were using them for, as well as how to problem solve testing issues using the data in the data sheet. This was discovered through trial and error while testing each version of the ADC. The final challenge faced was finding recommended parts as they were sold out or discontinued. This was solved through researching replacement parts and learning how to compare the important values between the options.
For the software side of the project, we also ran into a few tough obstacles. The first of which was that because we were coding directly onto the Raspberry Pi, we couldn't have more than one person writing code at a time, and it made working together extremely difficult. The best solution we found to this was to simply spend more time together in person and coding the program while sitting side by side. The next biggest issue was that some of our Python libraries became corrupt. This set us back an entire day due to debugging, research, various installations and uninstallations, and finally, an entire reinstall of the Raspberry Pi OS. Thankfully, this was a one off issue and we did not need to go through it a second time. The last obstacle I'm going to speak about was the sample rate. If the sample rate was too low, it would not read all the musical notes being played. If the sample rate was too high, it would read the noise that would occur between musical notes. The approach we took to fix this issue was trial and error. We simply kept going through different values for sample rate, chunks, and gain until we found the sweet spot where it was picking up all the notes we played while still turning the lights off when nothing was being played. The distribution of work for our project was fair from the beginning. We wanted to give each member an equal amount of work. The software design was left to the computer engineers, while the hardware design was left to the electrical engineers. We had Anya's primary task be the ADC, and Stefan's primary task was the preamplifier, with each person's primary task being the other person's secondary task. Next, we had the RGB integration as my own primary task, and the GUI was Carson's primary task. Once again, each member's primary task was the other member's secondary task. For the computer engineers, we had originally planned to create an entire application with more features. However, because there was a second team in the computer science department already making it, the plan became to integrate their application into our product. This goal unfortunately ended in failure because the Raspberry Pi 4 has an ARM CPU, which is not compatible with the program that the other team had created. We had many more ideas to implement into our project that we could not complete due to time constraint, fund constraints, and trouble with the ADC. Some of these are updating the program to include note intervals such as Perfect Fifth, which the computer science team had already implemented, a Bluetooth module to connect to and control a Bluetooth light strip in order to give the user more freedom of mobility instead of needing to stay within 5 feet of the box. Merging the computer science team's application into our own product, this will likely need to be done by rewriting their entire program directly onto the Raspberry Pi. A training mode that simply displays two colors, red and green. This mode will listen to the music being played by the user and display a green light if they're hitting a correct note and a red light if they're hitting an incorrect note. And finally, the most difficult feature to implement, polyphonics. This is giving the project the ability to continue to function as intended when multiple instruments are being played without picking up the sound from the other instruments. This may be possible using much higher end microphones, however, they were too far out of our budget for us to test this theory.